Hello everyone. First of all, a big thanks to ACM SIGDA, Microsoft and the organizers to host student research competition in ICCAD. I am Sumit from University of Wisconsin-Madison. Today I will discuss about my research towards efficient hardware architecture with optimized interconnect for DNNs. Nowadays, deep neural networks are used in many emerging applications like healthcare, avionics, virtual reality, autonomous cars, etc. Many of these applications are time critical. Out of all these applications, autonomous cars are one of the biggest inventions in this decade. In short, machines are driving the cars. But are these really safe, especially when few microseconds matter? What if an autonomous car miscalculates a decision on the road? Let us take this hypothetical scenario. When the signal is yellow, the car already crossed the stop line. When the signal is red, then it is on the junction. It may cause a fatal accident. Definitely, we need to reduce the reaction time of the autonomous cars, that is latency of the DNNs used in the driving algorithm. From our internal experiments, we found that the communication latency takes up to 90% of the total inference latency of the DNN. Therefore, communication is the bottleneck of the DNNs. I'll first explain how communication happens in the DNNs. In this work, we incorporate in-memory computing hardware since it has less number of memory accesses. In this type of architecture, first computations for several neurons are grouped into tiles. The tiles in different layers communicate through routers. We need to balance the communication with computation to reduce communication overhead. In this work, our goal is to obtain theoretical minimum possible communication latency with minimum number of routers and the links. This problem is very challenging. DNN sizes and properties vary in wide range. To tackle this problem, first we propose an optimization methodology to determine the number of routers required for each layer of the neural network. The input to the methodology is the DNN characteristics like number of layers, number of input and output activations, etc. The objective of the optimization is to minimize the latency. We put two constraints to the objective. The first constraint states that each layer has at least one router assigned to it. The second constraint puts an upper limit to the total number of NOC routers. This limit helps to put an upper bound on NOC area. This upper limit is a user-defined number. We solve this optimization problem through gradient-based interior point algorithm. We obtained optimal number of NOC routers required for each layer of the DNN. In the interest of the time, I am not going into the details of the formulation. If someone is interested, we can discuss more about it in the Q&A session. Obtaining the number of NOC router alone is not sufficient. We need to schedule the packets so that the communication latency is minimum. Therefore, we also propose a scheduling technique which minimizes the communication latency. Note that our proposed NOC architecture does not follow any standard regular NOC architecture. We prove by induction that the proposed methodology delivers theoretical minimum possible communication latency. We evaluate our proposed technique against a wide variety of neural networks. The number of layers varies from 5 to 100. The DNNs we consider also vary in number of parameters in a very wide range. Like ELINET has 0.28 million parameters and VGG19 has 45 million parameters. We observe that our proposed technique results in 74% improvement in communication latency with respect to a state-of-the-art methodology. This state-of-the-art methodology incorporates CMesh-based interconnect. CMesh-based interconnect uses a greater number of links than mesh to reduce latency, but it consumes more power. Therefore, with our proposed technique, we observe up to 6,600 times improvement in energy area delay product of the interconnect. Overall, our proposed methodology enables up to 25% improvement in total latency, which translates up to improvement of 1 millisecond of latency. Now we can trust autonomous cars because they are safe. Thank you.